Okay. So, in the last class, we have discussed topics up to conditional distribution and conditional density function. In this class, we will consider what is called total probability and Bayes theorem. Okay. After that, maybe an example will be taken up, a problem, and then I will switch over to another topic, a new topic, which is called function of a random variable. Okay. We will start that topic today. Okay. Suppose S stands for the set of all possible outcomes. Okay. And outcomes are like this: S1, S2, dot dot dot, say S m. There are m outcomes. Okay. Now, if we form, we already know that any subset of these constitutes an event. Suppose we consider some events A1, A2, dot dot dot, say AK, which forms a partition of S, that is A1, A2 and AK, they are mutually disjoint and their union is equal to S. In that case, as you have seen earlier, that for any arbitrary event B, we can always write PB as PB by A1, that is probability of event B conditioned to the event A1 times PA1 plus dot 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 dot, that is likewise PB by AK PAK, right. Well, let us for just probability, discrete probabilities, but we can use the same concept to derive the corresponding case for probability distributions. Okay. Suppose it is like this: x is the random variable. Okay. S, as I told you, is a set of all possible outcomes, and suppose there are k partitions A1, A2 up to AK. Okay. Then, following the same procedure, we can write that what is this? This stands for probability of the random variable x taking values less than equal to some given number capital X. Actually, this x less than equal to capital X denotes an event. That is, it is a set of all those outcomes for which the random variable takes values less than equal to some pre-specified value capital X. Okay. In fact, this is what we call, as we recall, f x x. There is a probability distribution of the random variable x. Now, we can write this as there is nothing new in this. We had just discussed the case for discrete probabilities, and we are just extending that concept here. Okay. Similarly, we can write we know that you can always write this thing, that P A by B is same as P B by A into P A divided by P B. This was discussed earlier. Okay. Again, we can use the same concept in the case of distributions, we can write P but this is nothing but conditional distribution of x subject to the event A. This is nothing but the probability distribution of x. So, this times P A. Okay. These are very useful results which you come across in various applications of statistics. Okay. We just consider an example here. I am following the book by Papoulis, as I told in the beginning, and it is a problem from Papoulis. This problem says that a fair coin tossed 3 times. Fair coin means, as you know, it is unbiased. Okay. The random variable equals the total number of heads. Obviously, x can be either 0 means in no occasion you got a head, x can be either equal to 1 means one of the 3 tosses gave rise to a head, other 2 tails, and likewise. Okay. So, the question asked is find the okay. So, we consider all the possibilities. See, there are three trials. Okay. At each time there are 2 possibilities, either head or tail. So, you can have 2 to the power 3, that is 8 possibilities. So, let us enlist them. One is T, T, T. In that case, random variable takes the value 0. Then T, T, H, it takes the value 1. Okay. Then T, H, T, again it takes the value 1. Sorry. It takes value 2, okay, because 2 H's have come. Then again HTT1, two, 2, and finally 3. Okay. So, the corresponding probabilities, it is not distribution, just the probability. This is a fair coin, right? This is unbiased. So, probability of t occurring on the first occasion is half, here also half, here also half. So, this probability is 1 by 8. Okay, how about this? Here H occurs once, okay, and T and T they occur twice. In this case, what is the probability? Okay, I think it might be a good idea to leave this problem at this stage. You know, I have just given a hint, and maybe towards the end I will take it up, because I find that I am not giving any problem for you to take up. So, I have gone up to this. So, I give you some time and you proceed with this, then we will take this up and we will work it out. Okay. You can easily start from here. Actually, the other reason why I did not pursue this is this, time being short, I wanted to complete this topic. I wanted to give a good coverage of this topic. Function of okay. Suppose x is a random variable. It means that some experiment is going on and there are several experimental outcomes. The total set is S. The various outcomes are S1, S2, S3 and likewise. With each outcome, with the experimental outcomes, a random variable x is associated. So, that for each outcome it takes a value. So, this is just repetition of what is the actual meaning or mathematical interpretation of this term random variable. Okay. Now, suppose I define a function y equal to g x, where g is a function. Okay. What does it mean? It means that given any particular experimental outcome, for that outcome this x takes some value, and g is a function which works on that value and gives you another value which is for y. Okay. That means, to tell you more precisely, suppose there is an experimental outcome say S k. Okay. For this, the random variable x takes a value, all right, for this. How is y obtained? We say y, in fact, we should write y is k, because y also is a random variable now. Okay. So, given the outcome, experimental outcome x k, what is the value for y? This is nothing but that is for the outcome x k, s k, find out the value x of s k, and g works on that. That is the value for y. Okay. Question is, if we are given the probability distribution function for x, how to find out the corresponding probability distribution function for y? Okay, that is a question. But before that, one thing is clear here, that if x is a random variable, obviously y also is a random variable. Okay, just there is some mathematical conditions that is required, that I just read out from this book. that is this they call that this function g should be a Bayer function. Meaning that given any value y for the random variable y, if you have to find out x or range of x, so that g x is less than or equal to y, then their range should consist of countable, the union and intersection of a countable number of intervals on the x axis. That is, if you take the x axis, it is not that there will be a continuous range, there can be various ranges and sub ranges, but total should be a countable number of union and intersection of intervals. Okay. And other thing is, the other thing is these events should have 0 probability. Obviously, this was one of the conditions for the conditions on a random variable, that is we should not have any outcome for which value of y assumes, for which y assumes the value infinity. So, that should have 0 probability. Okay. So, this event for which g x is plus minus infinity should have 0 probability. Okay. Then this y will be actually in the strict sense a random variable. Okay. Now, how to find out the probability distribution of the function y? For that, let us consider the let us consider what is meant by f y y. It is nothing but the probability of this event, where capital Y is some given number. Okay. This we know, this is very standard, this is the probability distribution of the random variable y. Now, we have to find it out given the function g and the probability distribution of x, that is we are given these two things, this function g and this is given to us. How to go about it? It is not very difficult actually, it is rather physically we can easily visualize it. We are given some number capital Y. We know this function g x. Given this number capital Y, we will try to find out for what possible values of the random variable x, the corresponding function g of x takes values less than or equal to y. Okay. We have to find out the probability of that. That will give us this function. Okay. I repeat again, we start with capital Y, okay, and we know that g of x is always y. So, we have to find out those ranges of x for which g of x takes values less than or equal to y, and then we have to find out the probability of those total probability of those values of x. Okay. That is how you should go about. I will illustrate this through examples. Then we will derive some particular relation, formula and all that. First, consider a function like this. this is g x, which is equal to y. Okay. Now, you have to find out the probability distribution f y y. First, suppose y is, by the way, look at this function, this is asymptotically touching b, it is not going above b, neither it is going below a. So, let us start like this, if capital Y x is given to be greater than or equal to b, then it is a very simple situation. The entire range of x gives rise to values g x which lie below capital Y, because it is never touching b, it is only asymptotically touching b. So, if y is either equal to b or above b, okay, then for any x in this axis, corresponding function will remain below y, and the probability of x in this total range from minus infinity to infinity, that is the total event actually, because x cannot take any other value, that will be 1. So, in this case it is very simple, f y, y will be equal to 1. On the other hand, you consider this, suppose y is less than equal to a. Now, here this function is asymptotically touching a as we go to minus infinity, as x goes to minus infinity, okay, but is never really touching a or never really going below a. So, if you place at y, if you take y below a, then this function remains above this for the entire range of x from minus infinity to infinity, it never goes below. In that case, f y y will be 0, because after all what is this? This means the probability of y taking values less than equal to capital Y. Capital Y is either a or less than a, and y, that is g x, is never going below that. So, the corresponding probability will be 0. These are very simple cases. Okay. Then, in fact, this is a new page, so I have to redraw the figure again, so I do it quickly. Now, suppose I take a value here y 1 and corresponding value here is x 1. Suppose y is y 1. In that case, what is f y y? Think for a moment and tell me. What is f y y? F y y means probability of this y taking values less than equal to capital Y, that is y 1. That is y should, small y should be either y 1 or below this. But you see, here I have y 1, corresponding value of x is x 1, and if you look towards the left of this x 1, you see for each x you get some value for y, but each value of such y is below y 1. So, to the the entire left portion of this point x 1 will give rise to values of y less than equal to y. This is very clear from the figure. So, that means this probability is nothing but this okay. But things may not always be so simple. Suppose I take another value now. In fact, I draw another figure because this is becoming clumsy. I take a value say here, call it y 2. Now, here you see this corresponds to 3 values of x, this corresponds to 3 values of x. Okay. One is here, another here, another here. You can call it x 2, x 3, x 4. Okay. In this case, what is f y y, where y equal to y 2, y 2 is shown here. You see, so you have to go below y 2, right. Now, as you go below y 2, you see, if we are in this range between x 2 to x 3, I have this portion of the curve, which is clearly below y 2. So, this is an acceptable range, but x 4 to x 3 is not, because within this range I have this portion of the curve which lies above y 2, but to the left of x 4 if we go, again the curve falls below y 2. So, that means I have to find out the two ranges for x which are applicable here are these, that is one between x 2 and x 3 or x 3 and x 2, another to the left of x 4, okay, to the left of x 4. All right. So, that means I have this probability is nothing but the probability of x lying within this range or lying to the left of x 4. Now, the probability of x lying in this range between x 2 and x 3 is, this we all know, f x 2 minus f x 3. Okay, that is what is this after all? This is the probability distribution of x, that is the probability of x taking values less than equal to x 2, and similarly probability of x taking values less than equal to x 3. Their difference gives the probability of x taking values within this range, and to that I have to add this f x 4. And likewise, you can consider various ranges. Okay, I have arbitrarily put y above, first above b, then below a, then somewhere here, then somewhere here. I mean, through this example, I am trying to show that given such function, you have to inspect the thing clearly, you have to consider all possible ranges, and then only you can find out the actual description of the corresponding probability distribution function f of y. Okay. I take further examples of this kind. A very simple example, suppose y is given as g x as a x plus b, very simple relation, just the relation of a straight line. Okay. So, suppose I plot it, it is like this. Okay, this much is b, because I mean, there is nothing particular about by choosing b to be negative, it could be here also. Okay. I have to find out the probability distribution of this variable y, this function y, okay, or this random variable y. That is, I have to find out as before this. Suppose I place my capital Y here. This gives rise to only one point in x, because this is a linear relationship, that makes life very easy here. Okay. Suppose the corresponding point is capital X. Then what is the probability distribution? It means the probability of y taking values capital y taking values less than or equal to capital Y. That means I have to go down from this point. But since it is a straight line, you can easily see here that if I go below capital Y, that means I go to the left of capital X. I go to the left of capital X. So, that means this probability is nothing but then this is expressed in terms of x, whereas I want an expression in terms of y. But this is quite clearly f x. Now, capital X is what? If you put capital X here, okay, but your starting point was capital Y. So, capital Y, that means what is capital X then? In terms of given capital Y, what is this point? We can easily see from this equation. The distribution is in terms of x. As I told you in the beginning, there are two things are given to us. One is the function g x, another the probability distribution of the random variable x. Only thing is I want the probability distribution of y as a function of y or capital Y. Okay. So, first I am finding out what is this. This in this case is f x capital X, where capital X is related to capital Y like this. Then I am replacing capital X by the corresponding value of capital Y, because capital Y is given. Okay, I am evaluating this function for a particular capital Y. So, this is this. But you know, the interesting thing is, I mean, if we stop here, then we only half do the job. As I told you in the previous example, we have to really inspect the cases thoroughly and consider all possibilities. Okay. So far so good, I mean there is no ambiguity here, but you see again things can change if I just I mean change some parameters or change just orientation a little bit. Let me explain what I mean. Suppose in this equation y equal to a x plus b, this variable a is negative. In that case, you have an equation like this. Okay. This is y, this is x. A is negative. So, if I now start with a particular capital Y, find out the corresponding capital X, then you see, after all our task is to find out this. That means, the probability of small y taking values less than or equal to capital Y. But if we go down, go below capital Y in this case, then unlike the previous case, we should not go to the left of capital X, because as we try to go to the left of capital X, this part of the straight line comes up which lies above capital Y, because slope is negative now, right. Please see this again, I repeat again. This means, this means the probability distribution of y, which means the probability of small y taking values less than or equal to capital Y. So, I have to go below to satisfy this definition, I have to go below from capital Y. But in the previous case, that meant that we should go to the left of this point capital X. In this example, that does not apply, because if you now go to the left of capital X for each x, the straight line, you can find the value of corresponding y, but that lies above this capital Y, the straight line that prevails above this capital Y. Okay. So, I do not have that range now. On the other hand, if I go to the right of capital X, the whole straight line remains below capital Y. Okay. So, that means I have to consider the range of x starting at capital X and going to the right. Okay. What is that? That is nothing but 1 minus, after all, what is f x capital X? F x capital X means the probability of x taking values less than or equal to capital X. That is the probability of the event small x falling in this entire range to the left of capital X, including capital X, or to its left. 1 minus that will be the probability of x falling to the right of capital X. And as before, this is given in terms of x, but I mean, I want a function in terms of y. I want a probability distribution function of y, I mean as a function of y itself. So, I replace capital X by this. Okay. We take another example. Okay, y equal to g x equal to x square. Sorry. Like this. Okay. We will find out now. Suppose we will find out this. Now, suppose y, or I made a mistake, sorry. Yeah, suppose y has value less than equal to 0, that is either at origin or less than that. Okay. In fact, I should say y less than 0, not less than equal to, but less than 0. Okay. In that case, clearly, I mean there is no range of x for which y takes value less than 0. So, in that case, okay. On the other hand, if we have some value of y, so I have got two values of x. Okay. In fact, one is x, another minus x, from symmetry of course. And what is x? Capital X, that is square root capital Y, and this is minus square root capital Y. So, what will be the probability of y taking values less than equal to capital Y? That is same as the probability of x taking values within the range minus x to capital X. Okay. That means let me quickly redraw again. This was your y, this is x, this is minus x. in this case what is the probability of x lying within this range? It is very simple, f x capital X minus f x minus capital X, right. And what is capital X? The square root 2 y. I put a plus sign here and then minus square root 2 y. Okay. So, through these examples you see that we really have to inspect the function. It has got various ranges, then certain parameter might change it, instead of taking a positive value, it can take a negative value, the whole shape of the function changes. You have to consider all those possibilities to come out with the probability distribution of the function, that is y. Okay. We still consider more cases. Now, suppose I consider a case where we are given y equal to g x, but there is a range of x for which suppose this takes a constant value. So, it has kind of I mean some kind of something like a table or DC is a region where it has a fixed value over a range. Then something interesting occurs, that is for the other ranges of x there is no problem, we can proceed as we have been carrying on, but we now suppose are given this, that for x less than equal to say x 1 and greater than equal to x 2, y equal to g x equal to some capital Y. Okay. That is within this range y is fixed. For this particular capital Y, what is the probability? In fact, it will be better if we just consider this instead of distribution. I am not considering distribution. What is the probability of small y taking the value capital Y? That will be better. What is the probability of small y taking the value capital Y? That will be same as the probability of x falling in this range. Okay, x falling within this range, and what is that probability? Sorry. Okay. Now, you see it has got an implication on the probability distribution f y capital Y. What is that implication? Suppose capital Y is fixed such that capital Y is say below this value. Okay, suppose I take a value of small y, capital Y prime, which is less than capital Y, and for that I have got some probability distribution function. Then as soon as I reach this capital Y, in the distribution function there will be a discontinuity, okay, because a total of this much will get added to the previous probability distribution function. Let me explain through some examples. Actually, in short, what I wanted to say is that at this point capital Y, this much. Physically, you can conceive also. Suppose I start with a very small value of this capital Y, okay, and as I take higher and higher value, this probability distribution increases, because it is after all a non-decreasing function, as we all know. Okay. Then the moment I reach here, okay, then since the function g x was static that time, it was constant, this amount of this is an extra amount that gets added to that probability distribution function, and then as y moves above this capital Y, I again continue to get this probability distribution function in a non-decreasing manner. Okay. Maybe I take an example. Consider this case, a very simple case. It is given g x is x minus c for x greater than equal to 0 and equal to x plus c for x less than equal to 0. In fact, to be very correct, we should write 0 plus and 0 minus to indicate the right side of 0 and left side of 0. Okay. Interestingly, you see this function has one zone from minus c to c, where it has got a constant value of 0. This is given, and the other thing that is given is, I go to the next page. Something like this. This is given. You have to find out the probability distribution function of y. Okay. Now, just for the sake of convenience, let us draw that figure here again for g x. Okay. And we are finding out this. Suppose capital Y is to the left of this side, left of minus c. Okay. Sorry, capital Y is above, below 0. Suppose capital Y is below 0. Okay. That means we are on this side. Okay. We are on this side, to the left of, I mean, the range of x falling to the left of minus c. For all of them, I have got this, the function g x given by this line, which is below this axis. Okay. So, that means, if y is less than 0, the corresponding probability distribution will be what? The net probability of x falling in this range. Okay. Net probability of x falling in this range. That is after all, the straight line equation is x plus c, okay, and capital Y remaining in this range means x should be less than equal to y minus c. Okay. If sorry this is nothing but f x y minus c. Okay. This is for y less than 0. For y less than 0, this is the thing. But what happens when y is greater than 0? That time, again I redraw these figures, so that I do not have to go back to the previous page. In this case, if y is greater than equal to 0, then I am to the right of c. So, the probability of x falling to the right of c, okay, what is that? In fact, it is not like that. If I am giving a particular value, say capital Y, y is here. Earlier I took y to be below 0, say y was here. So, corresponding x was here, and as I go below capital Y, the entire range to the left was considered. Okay, and like that I derived the previous probability distribution function. Now, suppose y is above 0 somewhere here, then I am here. Okay, I have to find out the probability of x falling in this range, either at this point or to the left of this, if you call it capital X. So, the point is, if you consider this total range, the probability of x falling in this range, okay, that will be related to probability distribution of x. Now, if this capital X were here or here or here or here, then it simply becomes the probability distribution of x. But as we cross this, okay, as we cross this, I mean x increased, but y did not increase. Okay, so, an extra component came in. In fact, if you really work it out, it will be like this. Because here the straight line equation is x minus c. So, x when expressed in terms of y is y plus c. So, x should be less than equal to y plus c. Okay, given a y corresponding point is y plus c. So, x should be less than equal to that. Okay. And that is this. So, if you plot it, since this function is given f x, using that you can plot, and then instead of going to another page, I can carry out the plot here only. If you plot it, it will be like this. This portion will be taken up for small y going up to 0, and then from 0 upward, from 0 onwards, I mean for values greater than or equal to 0, portion to the right will be taken up. Okay. So, it will be nothing but nothing like this, then there is a discontinuity, and then this portion will come up. Okay. This is your f y y. So, in this class we have we just concluded our previous topic, that is conditional probability distribution and density functions. We give the expressions for total probability distribution and of course, if you derive that with respect to x, if you differentiate that with respect to x, you get the corresponding total probability density also. Then we took up an example, but I did not carry out, I left it to you. In the next class, I will take it up. Okay, I hope you also will be able to come up with a solution by that time. Then subsequently, I took up a new topic altogether, which is called function of a random variable. Okay, we defined what is meant by a function of a, we explained what is meant by a function of a random variable. Then our purpose was to obtain the probability distribution function of that random variable y, which is written as a function of given random variable x. Of course, the distribution was carried out, was obtained from a knowledge of the function g x and from a knowledge of the probability distribution of the random variable x itself. So, we considered various cases, okay, and various possibilities, and in the next class we will continue from here, okay, and we will try to obtain a general formula, of obtaining the probability distribution function of the probability distribution of the function y itself, okay, expressed as a function of y. Okay. So, that is all for today. Thank you. Okay. In a previous class, we considered a problem, then I was working it out, but then I left it halfway through. I thought you would give it a try. So, let us solve that problem first, and then we will consider the subsequent topic. The problem that I gave was this, that there is a fair coin, means the probability of having head or tail, in either case is half, and then coin is tossed thrice, and the random variable x equals the total number of heads. Okay. So, I have to find out the probability